So do I call you Nagar or Azam or
As you want, doctor. My name is Azam. My family name is
Azam? Then
Nagar.
it's okay. I call you Azam then. Okay.
Yeah. Okay.
All right. Could you please confirm if you can see the slide on the screen?
Yeah, doctor, we see.
All right. Thank you. Thank you. So today we'll move on with conductivity. Okay. We've discussed a calculation yesterday on J drift, right? So J drift, and we've seen that J drift is contributed by both electron drift and hole drift, but the final magnitude of the J drift, or the final value of J drift, will be dependent on whether your doping concentration is on the high side or on the low side, right? So yesterday we've seen in the calculation, let me just show the page again, that when your P, or when your hole is negligible, in this case, P equals to 10 to the power of minus 4, right? Relative to the 10 to the 16 for N, right? So then the contribution of the whole drift will become very, very small, or you can say that it's negligible, okay? And therefore, the final J drift value is dependent purely on the contribution from the drift of electrons, as given by NQ mu E, okay? NQ mu E times electric field, okay? So I hope you understand that. So today we're going to move on to look at conductivity, okay? So conductivity, as we discussed earlier on when we started the class, it is the inverse of resistivity, okay? It's the inverse of resistivity. It is denoted by a sigma for conductivity and rho for resistivity, okay? So the equation is given here. Rho is 1 over conductivity, and therefore we have seen before that conductivity is equal to mu of your carriers times the carrier concentration times electronic charge, okay? And you can break those down into two parts, which are the contribution from electron and contribution from hole, okay? And again, you can use either mu n or mu e, mu p or mu h. As long as you're consistent, it's totally fine, okay? So below here, you can see the graph of resistivity on the y-axis against impurity concentration. So we've also discussed this when we talk about our previous topic, when we're talking about resistivity against doping concentration, okay? And we have discussed last time that, for example, if you're given a silicon wafer from a cassette that is already labeled, you can tell the doping concentration in that wafer by looking just at the resistivity value of the wafer, okay? For example, if you are working on a p-type wafer, for example, and the resistivity given on the label is 1 ohm cm, 1 ohm cm, which is there 10 to the 0 on the y. So you can then just see the corresponding value of your p-type silicon, for example, which is somewhere there, 1.5, about 1 to 2 or 1.5, pretty much 10 to the 16 of doping concentration in p-type for silicon at room temperature, okay? So yeah, it's as easy as that. You know the resistivity, you can then come to this curve every time and check out the doping level that you have in the wafer, okay? And the same goes for N as well. Same goes for other doping level as well. You can check if you're working on, say, 0.1 ohm cm, then your corresponding doping level will be early 1017, for example. But if you're working on a more resistive wafer, for example, if you're working, say, at 10 to the 2, which is very, very high, 100 ohm cm on the Y, sorry, 100 ohm cm on the Y, then you're talking about that level, early 10 to the 14. Okay, so you can also see and the doping concentration for different semiconductor materials. For example, on the right, you can see gallium arsenide, P-type and N-type. You can see germanium, right? You can see gallium phosphide for both P-type and N-type at 300 Kelvin as well. Okay. So from there, you can tell the level of doping concentration in the wafer. Okay, without even measuring the wafers. Well, if you want to go and measure and characterize, for example, if you want to recheck on Hall effect, we're going to learn on Hall effect shortly. You can also take your wafers to do the Hall effect measurement and verify whether the reading is really reflecting the doping concentration as expected from the resistivity value, right? You can do that as well. So a bit on resistance and its connection to resistivity. Resistivity and conductivity are related. They are inverse to each other. We've learned that. And you can also look at conductivity to be equal to 1 over resistivity or J over E. Okay. And then from here, the resistance, I believe you've learned this one last time on in electronics, perhaps. Ada belajar kan? This equation R equals rho L over A in electronics. Do you learn this in electronics last time? It's one of the basics in electronics. Ada ke? You learn this in electronics 1 or 2?
Yes, Dr. Got.
Yep, okay, good. So R here, the resistance of a slab of semiconductor. It can be silicon, can be germanium, gallium arsenide, gallium phosphide, whatever. A slab of your semiconductor material. The resistance is given by rho L over A. Rho times L over A. Rho is the resistivity. L is the length of the semiconductor slab. A is the surface area, which forms the channel, if you like, macam channel, which form the area consumed or used by the carriers to pass through. Okay, and then JE here will be the current density related to the slab. Okay, so let's just do a simple calculation here to relate or to demonstrate the relationship between these important parameters. For example, so the concentration of donor impurities, okay, the concentration of donor impurities in silicon is ND equals 10 to the 15. Okay, so again, silicon, let's just recap. So what is the majority carrier in your semiconductor now? That's what we did yesterday. So what is the majority carrier in your semiconductor now, in your silicon now? Azam, what do you think, Azam? What is the majority carrier in this case? Is it electron or hole? Azam?
Doctor, I think it's electron.
Electron, right? Okay, electron because it's donor concentration, okay? So the silicon is doped with either phosphorus or antimony or arsenic from group 5, pentavalent atoms, right? So therefore, you're going to get extra electrons for every incorporation of whatever atom, phosphorus atom, for example, from group 5. Okay, so so what is then the value of N? What is the majority carrier concentration? What is the doping concentration, or what is the carrier concentration in this case? What is the value of N in this case? Anyone? Okay, 10 to the 15, right? Very straightforward, just like what we discussed yesterday. Okay, sama ya. So I just would like to repeat to make sure that you have your grip on that, right? N is now equals to 10 to the 15. So if the question is asking what is the value of P, what is the value of P in this case? Anyone? What is the value of P then? 10 to the 5, isn't it? So straightforward, huh? Law of mass action, isn't it? Ni squared over N for P, yeah? N times P equals to N squared, okay? So if you have this question every single time, you should be able to tell already, right? You don't even have to press your calculator for this. As long as you know it's silicon and there's no number in the front of 10 to the 10, it's very straightforward, right? 10 to the 15, therefore 10 to the 5. 10 to the 16, therefore 10 to the 4, and so on and so forth. Assume an electron mobility of mu n of 1,300 centimeters squared per volt second, and a hole mobility of mu p 450 centimeters squared per volt second. Calculate the resistivity of the material as your question number 1. And therefore, the second one is conductivity of the material, which is the inverse of the first. So this is a very simple question, right? You shouldn't miss this one. Senang ya. So what you have to do is just plug the same equation, plug the equation for the resistivity. So where resistivity is equal to 1 over 1 over conductivity, right? And the conductivity is equal to Q or E. You can use either one as long as you're consistent. E times mu n times nd. That's it. Q or E 1.6 times 10 to the minus 19 times mobility under 3,000 and nd equals 10 to the 15. And you got 4.81 ohm cm, right? 4.81 ohm cm. None, that's it. And the conductivity is therefore the inverse of resistivity, which is 0.2, the inverse of the same unit, right? Ohm cm minus 1. Okay. Okay. And any question on this? Is it okay? Too easy, right? Yeah. Okay. Good. Simple. Right. So let's go to the next question. A silicon, again, silicon. So below silicon, you can already plug in N1, Ni 10 to the 10 per centimeter cube if it's required, right? A silicon sample is 2.5 centimeter long, right? The L is 2.5, has a cross-sectional area of 0.1 cm squared. The A is 0.1 centimeter squared. The silicon is N-type, right? Silicon is N-type, doing impurity, Nd equals to 2 times 10 to the 15, okay? 2 times 10 to the 15, and the resistance of the sample is measured and found to be 70 ohm. Okay, R is given. What is then the value of electron mobility? Okay, sama je equationnya just rearrange to get this mobility value, right? So what you have to do is you know that R is equal to rho L over A. L is known, right? And then conductivity over A, because rho is 1 over conductivity, and then you will arrive at this equation, L over Q or E times mu times N times area, right? Or you can then rearrange that as mu because you're looking for mu, right? So then you're going to get L over Q times ND times R times A, and the rest are all given, right? L is known 2.5, Q is known, a constant, N is given, R is given, it's already measured 70 ohm, and A is given. And therefore the mu will be 1,116 centimeters squared per volt second, right? Sama aja, it originates from the very same equation. Then we just expand the conductivity, resistivity, sorry, to be the inverse of conductivity, and we plug in all the important parameters in the conductivity equation and just rearrange and replace, and that's it, right? So you're gonna get 1,116 centimeters squared per volt second, right? Any problem in this? Everyone can understand? Okay, too easy, still too easy, right? Okay, good. Right, so now let's move on to diffusion. Okay, we're going to see diffusion, and we're going to see some animation as well, just like the way we did for drift. So diffusion, we have discussed earlier on that diffusion is there if you have concentration gradient between two neighboring regions. Okay, under two different spots or two different locations, they should have concentration difference, which we call concentration gradient, for the carriers to diffuse across the region. Okay, if there is no concentration gradient, there will not be any diffusion across the two different regions because they are already at equilibrium, if you like, right? So diffusion is the process whereby particles flow from a region of high concentration towards a region of low concentration. So it's high concentration region to the low concentration region. Okay, so the one on the left is occupied, which is high concentration, and the one on the right is empty initially, which is low concentration region, right? You may also have some diffusion if you have something like this. Perhaps you have two particles on the right and 20 particles on the left. You're still going to have concentration gradient as well because you don't have the very same number of particles on both sides. So if the gas molecules were electrically charged, the net flow of charge would result in a diffusion current. Okay, so if your particles are charged particles, so in this case we're talking about electrons and holes, which are charged particles, then there will be current density associated with the diffusion process, just like the way we have the drift current density associated with the drift of electron and hole as well. Okay, so let's just see on this link. Let me just unshare. I think this link was already updated on the website. Let me just go back to the website and share. Bear with me for a minute. Just open the link. EV education. Hold on, yeah. EV education. Okay, let me share on the screen. EV education is here. Okay, can you see the website on the screen? I'm just about to open though.
Yes, doctor.
Okay, good. So let's search for diffusion then. Where's diffusion? Doping. Ah, yeah. Diffusion is here, chapter 3. Just beside drift. Right, so now you're on diffusion page. So you can see here the diffusion will take place the moment you have a concentration gradient between two or more neighboring regions. Okay, the moment you have regions with different carrier concentration, you're going to have diffusion. So let's have a look at this animation first. Diffusion is the random scattering of carriers to produce a uniform distribution, or rather random movement of carriers. Okay, well, along the way, along the movement, you may have scattering as well along the way, right? So let's just see from here. In this animation, a quarter of the carriers move to the right, a quarter to the left, and the remainder stay put. So let's just see from here. Start. You can see net movement of carriers. We started off as a high concentration region in the middle, and then you have an empty region on the left, empty region on the right. So therefore, you should expect movement of carriers to the side as well in order to fill the whole area with uniform concentration. Okay, so that's why we're saying net movement to the left and the right. Okay, so you can see more and more, and they are experiencing some scattering event as well. Right? The carriers continue to diffuse from high to low concentration region. Okay, so keep moving. So along the movement, there'll be some scattering between the particles themselves, right? Process continues until uniform concentration results, right? Until you have a uniform distribution of particles in all the areas, okay? So let's see now. No, this is the update, I think. Let me just see this. Okay, this is the movement. Just to illustrate random motion. So let's see from here. The holes and the electrons. Holes are blue, electrons are red, move from the areas of high concentration to low concentration within a semiconductor towards an even distribution. Okay, bear in mind that the aim or the final step will be even distribution, right? The moment we have achieved even distribution, the diffusion will stop. Okay, so we start off with electrons on the upper right, on upper right here, and we start off with holes on the bottom left, and then you're going to see diffusion of the carriers of both carriers to fill the whole region here. Okay, let's restart. Okay, let me see if there are any more animation here. Now the rest are all equation that we're going to cover later on. Yep, so you can see that. Let me just go back to the slides and you can have a look for yourself later on the website and play with it. Okay, so having seen the examples of diffusion, can you perhaps give one example of a diffusion process that you normally see in your everyday life? Right? Give one example. Think of one example. I'll give you like 10, 15 seconds perhaps. Uh, can you try to recall or try to think of one example involving diffusion of particles or diffusion of particles in your everyday life that's easy to explain or easy to relate with our previous animations? Anyone can think of anything? Any simple examples which involve diffusion, but we've probably have taken it for granted because it's too simple in our everyday life. Can you think of anything? Anyone? Ada satu simple example yang very very simple. We do it almost every day, but perhaps we have never think about that. Anyone can think of anything?
I think Doctor like tea when you meet the tea and
Exactly. Can you explain a bit, Azam, on that? How is diffusion taking place in your preparation of tea?
uh, you know when you have just a hot water and then you put the tea and
Yeah.
then the tea and later on you will see that all the glasses become red like the tea color.
Okay, right. That is very simple, isn't it?
Yeah.
Simple, and yeah, we perhaps take it for granted because it's too simple. So when you started making a tea, just like what Azam said, we pour in hot water and then later on tea bag or either way. Okay. Let's say you just pour in hot water and then tea bag follows. When you started, what is the color of the water in the glass? Clear, right? It's a clear water, isn't it? Because you
Yeah.
just started and the diffusion just starts to take place. And where is the high concentration gradient in this case? Azam, since you're talking about concentration gradient, where's the region of high concentration in your tea?
Uh, will be in the tea bag like if I mentioned
Right.
the tea
The
bag.
high concentration or the
Yeah.
particles will be a lot higher in the tea bag. And the low concentration gradient, if you look at this schematic on the right. So this one will be your tea bag on the left, and yang kanan ni on the right will be your hot water. Okay, and then eventually when you whether you stir or not stir, if you don't have a spoon and stir, it will still diffuse anyway, right? If you don't stir, for example, it will still diffuse anyway. It's just that it will happen at a slower rate, it's going to diffuse anyway. You're going to see your water changes its color from clear to yellow, and then perhaps brown, and then orange, and then perhaps red, depending on the tea, of course, right? It's going to happen anyway. But the rate is going to be a lot faster if you stir, right? If you pour in hot water and you use your teaspoon to stir, then you're going to get faster, right? Faster tea prepared, okay? So that's one of the simplest examples that we can relate to diffusion. And the rest here, Bala said perfume. Okay, perfume. And then, who said, yeah? Zul say breathing. Okay, Bala, would you like to elaborate a bit on perfume? How's that diffusion?
Because perfume, even if someone places perfume in one corner of the room, eventually the person in the other corner of the room can smell it because perfume at one point is high concentration gradient. There's a condensed chunk of
Right.
perfume at one point, so eventually it will diffuse and spreading across the room. The person on the other side can smell it.
Yes, good. Just like the animation we saw on the page, right? Where you introduce electrons on one side, holes on the other side. So you can just imagine those electrons are like your perfume particles from a perfume. And then it's going to diffuse eventually throughout the whole lecture hall, perhaps, right? Good. So breathing, how's that diffusion? So can you relate that to diffusion? Breathing. You mean breathing out, right? Rather than breathing in, or both? Okay, let me see the process of oxygen in the lung. Okay. Oh, it's not that direct. Can you elaborate a bit? For example, kalau you ambil your example could be something like you exhale, and then if you want to relate to COVID, perhaps, wearing mask. Kalau you sneeze, perhaps, right? And then it's going to diffuse to some other neighboring person, right? Yang dekat, and then that's why you want to block by mask. You don't want the particles to be moving in the region, right? In the neighboring region. Okay, so those are simplest examples of diffusion. Okay, so let's just continue for the next 5-10 minutes. I need to stop earlier today because I have a meeting at 10. Oxygen concentration in the blood is much lower in the lung. Okay. So it's between the circulation of the blood, okay? Diffuse into the blood, oxygen in the lung, right? So that's the elaboration. So let's just move on for the next few minutes. So diffusion is the movement of electrical charges due to presence of a concentration gradient. Just like what we discussed now, the breathing, the perfume, the tea, right? So those are the simplest examples. But in this case, we're talking about electrical charges, right? Since we're talking about semiconductors, so we're talking about electrical charges, which are electrons and holes. The current density is the flux of charge carriers. So if you're working on just particles, then there's no current density associated because it's not charged. But the moment you're talking about charge carriers like electrons and holes, there'll be current density coming along, just like what we discussed on drift. And the current density for this diffusion is called diffusion current density, due to the hole and due to electrons. Okay, just like the way we discussed J drift electron, J drift holes. Now we're talking about J diffusion electron, J diffusion holes. And J diffusion of holes is given by Jx, the first one, Jx equals to negative sign for holes, QD electronic charge time diffusivity times the concentration gradient, dpdx, okay? dpx dx, right? Similarly, for electron will flow if there's a gradient in the electron concentration as well. Just the way that we saw on the animations now. The moment you introduce both the carriers on both sides, they are going to diffuse and reach uniform distribution eventually. So for J electron, you can say Jx. You can even label this as J diff hole, J diff electron. It can be done as well. So negative Q, which makes it positive, times D diffusivity times D nx dx, right? So D is the flux, is related to the flux of the gradient of the charge, and it's called diffusion coefficient or diffusivity. same thing. Diffusivity, ya, ataupun diffusion coefficient, either one is fine, and has a unit of centimeters squared per second. Diffusion occurs whenever there is a concentration gradient and particles are in constant random movement. Okay, so this will be the equation that we're going to use. So let's now have a look at the direction. Okay, you can see the graph of electron concentration on the top, hole concentration on the bottom part. Okay, so electron flux. Okay, if you have electron flux moving to the left, if you have electron flux moving to the left, you're gonna get electron diffusion current density moving to the right, pointing on the opposite direction. Okay, so X here is the depth or the space that you have where the motion is happening, right, of carriers. And the same goes to if you're talking about your whole movement to the left. This is just an example, okay? In the real case later on, when we talk about p-n junction, you're gonna see opposite direction between holes and electrons. So if you're looking at hole moving to the left, you're gonna get hole diffusion current density moving to the left as well, because whole movement is in direction of the current. Okay, and the same goes here. It's the space. So diffusion, when you have diffusion, you can say this as your concentration of particles, whether electrons or holes, against distance on the x-axis. So the moment you have your carriers diffuse to the neighboring region here, assuming move to the right, net movement to the right, so you're going to see at different times T1, then later, a bit later T2, a bit later T3, you're going to see the profile of the electrons or of the particles, for example, changes this way, right? It's going to get like that, like that, like that, like that, like that, sampai dia achieve uniform distribution across. Okay, so it's going to get lesser and lesser concentration on the starting point, and it's going to be more distributed across the space. Okay, so generally DE and DH are different, diffusivity of electron hole are different. However, the diffusion coefficient and the mobility mu are related by thermal voltage, which is Vt equals to Kt over Q. And Vt is about 26 millivolt at 300 Kelvin at room temperature. Okay, and these can be related by this equation that we call Einstein relation. Okay, Einstein relation states that when you're going to have D over mu, your D over mu of your carrier, electron or hole, will be equal to Kt over Q. Okay, your diffusivity over mobility equals to Kt over Q. K being Boltzmann constant times temperature over electronic charge. And the same is true for hole as well. Okay. Well, let me just stop here for today. Then we are going to continue later on, right? So I need to run for a meeting next, so I need to stop earlier today. So is there any question on diffusion or on the previous calculation that we did? Is it clear so far on diffusion? Any questions? We're gonna do some calculation as well, yeah, later on, okay? You can try for yourself first, and then we're gonna finish off with Hall effect, and then we are ready to move into the next topic, which is generation and recombination. Okay, any questions so far? All good? Tak ada? Okay, kalau tak ada, then I'll see you in our next class. Bye-bye, take care, Assalamualaikum. Sorry, I need to finish earlier, yeah?